Yeah, so let's now move on to combinations. So we just talked about permutations. Now let's like talk about something that's very similar to permutations, but it's slightly different, which is something called like a combination. So notice that the important thing in a permutation is that like the order in which you choose the objects matters, right? So, um, like for example, if you had like objects like A, B, and C or something, uh, like let's say you had like those 7 objects, and let's say A, B, and C were our 3 objects that we chose. Then we counted A, B, C as a different permutation as like, for example, CBA. Like if you're like arranging the 3 objects in a line, you counted these as like different objects. Now, like what if like we don't care about the order? All we care about is like how many ways are there just to select 3 objects, or let's just select objects from a subset of objects from a big group of objects. Like we don't care about the order. Like in permutations, we cared about the order, where we like what object came first in line, what object came second in line, and so on. But maybe there are some times when we want to know like how many ways there are to simply choose objects without regard to the order in which we choose them. So this is like how combinations work. This is why combinations are important. And it turns out like combinations are very similar to permutations. And to like solve this, let's say we again had the same problem. We had n objects. How many, and we want to ask how many ways are there to choose k of these objects. And the important thing this time is like we just want to choose them. We're not going to like order them in any way or something like that, like put them in a line or something. We just want to choose them without regard to their order. So how we could do this is like we know that like there are n factorial divided by n minus k factorial ways to like arrange these objects if the order does matter, right? This is what we just found like in the box up here. Like we just found like this is a number of ways to like select k of these objects from the total of n and arrange them in a line where the order matters. So this is the permutations. But like luckily this is pretty easy to fix because if you have, once you choose k objects, so let's say like k equals 3, for example, just to make it easier, just to like give us like specific numbers just to make it easier to work with. So let's say our 3 objects were like A, B, and C. We call them A, B, and C. In the permutation, we overcounted it by like some number, right? For example, we counted the arrangement ABC different from like ACB, BAC, BCA, CAB, and CBA. Right? In the permutations, we counted all of these as different. But in the combination, we want to count this as the same because we're essentially just choosing the same 3 objects. Like we don't care about the order. So notice that like there are 6 ways to like kind of overcount this by. We're kind of overcounting it by 6. And notice that 6 is just 3 factorial, which makes sense because like because you're overcounting it by like 3 factorial because you're like arranging 3 objects. So in general, if in this case, for example, if we wanted to count everything exactly once, we could just divide by 6, or just, in other words, divide by 3 factorial to remove the overcounting. So in this case, we use 3. In the general case, we use k. So if we wanted to remove the order restriction, we would just divide by k factorial. Like we would take the permutation thing and divide by k factorial. So we would have n factorial over n minus k factorial, which is a permutation. Then you divide it by k factorial, that represents the combination. So you can kind of move the k factorial to the denominator. This is n factorial over k factorial times n minus k factorial. And this is like the, like this represents the number of ways to just simply choose k objects from a total of n objects. So does anyone have any questions on like how this combination formula or derivation worked? Okay. Let me just like show a quick example just to make sure like we understand. Oh yeah, and I should also mention this expression in the box, as we just saw, that this represents the number of ways to like select k objects from a total of n without regard for order. This like expression is so important in combinatorics. Like it's probably one of the most important things in combinatorics. Like you'll see it over and over again. So like we give it a special name. We see this is n choose k. So you write like n choose k. You write like n on the top, k on the bottom, and you put like kind of like parentheses around them. They're not really parentheses, they're like, well, they kind of are. So it's kind of like a fraction without the fraction bar, without like the, this, but like, it's just n choose k. And you would read this as n choose k, like choose. So like this is very important in like combinatorics. So you'll probably see this notation n choose k very frequently. Sometimes you might see like n like ck or something like that. Like there are many different like notations to express the same expression, but most commonly you'll probably see like n choose k with like parentheses around it. They're not really parentheses, but you can think of it like that. So just to give like a concrete example, let's say you had like 7 objects. We want to select 3. Like without regard to order. Like let's say we had like 7 objects in a bag, and we just want to take 3 of those objects from the bag. So like we're not going to do anything with them. We just want to see how many ways are there to just take the 3 objects. So we can just kind of use the formula we just derived. This would represent 7 choose 3 using the notation we just talked about, right? Like 7 objects want to choose 3. Using this formula, this is 7 factorial over 3 factorial divided by 7 minus 3 factorial. So this is 7 factorial over 3 factorial times 4 factorial. So I can write 7 factorial on the top as 7 times 6 times 5 times 4 factorial divided by 3 factorial times 4 factorial. So these 4 factorials kind of cancel out. So 7 times 6 times 5 divided by 3 factorial is 3 times 2. 3 times 2 is 6, so these cancel. So this is 35. So 35, that means there are exactly 35 ways to just select 3 objects from a total of 7 objects. Yeah.